Thank you for the introduction, and thank you for you to keep being interested about topological data analysis. Although we have already heard several talks about the topic, so I try to focus on aspects which are different in our work from what you have heard so far. But in any case, let me start with a brief recap of our work, which is joined with Sam McArdle and Berta. So. Just brief recap. In topological data analysis, we are assuming that our data comes from some manifold. There is some underlying manifold, and we are sampling data points from that. And although we only get points, we aim to understand the structure of this manifold underlying the data and learn from that. So this is a machine learning inspired or data analysis method, which focuses on the shape of this data set and underlying space. And the good thing about this approach to data analysis that it's quite robust, invariant under rotation, and so small local stretches don't really affect that much what we see. So that's a huge advantage of looking data at this topological level. And so the way we uncover the structure from a few data points is that we connect two points if they are closer than some specified distance. And that's how we get an edge. But then we continue a triangle, which is 3 points. They are also connected and they are filled with a simplex. If the points are all connected, so it's a clique. And similarly, if you have a 4-clique, like a tetrahedron, or a higher dimensional clique, then if all the edges are present, then you fill it with a simplex of the appropriate dimension. That's how you think about this, and that's how you get from points to these more continuous shapes. And so it is somewhat robust to local stretches and so on, but not entirely. For example, if you have an object that you scale all together, actually, then the Betti number is not invariant. So look at this line segment, which is and its length is epsilon, which is the length scale at which we wish to connect things together. And in the first case, when I have this, I don't know, very just toy example data set where the vertices of these triangles are the data points. Now we connect which are close to each other, and we get 4 triangles filled. But the square in the middle, the opposing points are too far away, so they don't form a 3 or 4 clique. Therefore, that's a void, that's a hole-like object there. However, if I just scale the entire data set by a factor half, now suddenly everything becomes close apart and everything is filled. So whereas at one version of the object has a hole, the other version doesn't, although topologically they should be the same. So that's an issue with looking at a single Betti number. So that's why it's not necessarily informative enough to look at a single Betti number. And so a solution to this is determine the number of holes, the Betti numbers, at different length scales. So we choose epsilon, different numbers, and that gives us different shape holes, and we determine them all together. And so this is called persistence, and there is one extra thing. Actually, you can even track the holes. So maybe there is some length scale where the above points are all disconnected. There is no holes because there is not even continuous shape really formed. And at some point, the middle hole appears, and for some length scale it is alive, and then at some point it will disappear because it gets filled. So the persistence is really tracking the holes as they appear in the object and how long they live until they get filled by choosing larger length scale. This is the idea of persistence. And if you have a persistence diagram, which I will show you soon, then rescaling of the original object is just a shift of this diagram, so it really is largely invariant under such scalings. So here is an example of a persistent diagram. So you have your data points. Initially, if you just consider a small region, then they are all disconnected. And eventually, as you look at bigger and bigger distances, then some line segments start to form, and then eventually also a cycle forms. Then a bigger cycle forms, but then the smaller cycle gets filled, and finally everything is together and everything is filled. So in terms of, you can track the number of components. That is one possible thing that you can look, or in this number of holes, the Betty numbers, that would be these two-dimensional holes. And you can see this is, at this length scale, this circle appears, and at this length scale, the circle gets completely filled. So this is the persistent diagram for that particular hole in the data. And this is for this large cycle. And so in practice, when people use this topological data analysis for classifying data and so on, then they actually use diagrams like this and do machine learning later on these diagrams, because it tells you a bit more about how your objects appear and live. Maybe you want to say that if some hole is just very short-lived, then maybe it's just some sort of noise. Really, the robust topological features, they should be holes which are present for a very, very long change of scales and get filled only at a later time. So maybe you filter this to only look at the long enough holes or something like this. This is what people do in practice. And so the whole theme of our paper and our work is that we want to understand if this topological data analysis as a machine learning primitive, when is it useful? When do people actually use it in practice? And for that set of parameters, which are relevant for actual practical tasks, are there any quantum speedups? And if they are, how big are they? So that is the main focus of our talk and work. And this is different from the previous one, where Berta told us examples when you have, these are not yet practical examples, but very interesting ones, where you have a very large number of holes. And that's where we can hope for a bigger quantum advantage. And if we want some exponential looking speed up, then we should look for that kind of edge cases. But to us, it seems that the currently used data analysis techniques usually look at other kind of, like in practice, you have a small number of Betty numbers. Like in this example, we have 2 Betty numbers, whereas many, many simplices. So these are the kind of examples which we saw in the literature. So we try to understand what's the speed up we can get for this kind of examples. Well, before going into a bit more detail about how the algorithm works, a very key concept is the boundary map, which helps us understand these holes in a linear algebraic fashion. So this boundary map, dk epsilon, this maps a k simplex, which is a k plus 1 tuple of points, which are click at this length scale that you look at, and epsilon here refers to the length scale that we are at currently. So it maps a simplex to linear combination of its faces. It's also, if it's an oriented simplex, simplicial complex, that is the case in data analysis, then there is some signs that you put in front of this linear combination that that somehow give information about the orientation. And well, if you define your boundary map this way, then it actually tells you information about the number of holes. And one thing that we need to consider here is that the boundary operator can be defined just as mapping simplices to its faces, but now we care about its connection to the actual object that we have, so we need to restrict this boundary operator to the valid set of simplices. And so this is the actual boundary map we deal with. We restrict it to the simplices of the manifold. And using this boundary map, we can compute the Betty numbers using the following formula. The number of holes or Betty numbers for the k-dimensional holes is the dimension of the kernel of the boundary map minus the dimension of the image of the boundary map, which is acting on one larger simplices. And so the idea here is that somehow the boundary map and its kernel somehow counts whole-like objects, whereas whereas the simplices that come from one larger simplices under the boundary map, those are kind of filling up some whole-like objects. So if you want to understand which are the holes that are not just potential holes, but actual holes in your manifold, then you need to subtract this. This is the rough idea why it is like that. And now, a very similar thing can be said for these persistent Betti numbers. So these would be Betti numbers that are already holes at length scale epsilon, and they are still void at length scale epsilon prime. But you need to modify. You still start with whole-like objects, which is the kernel of this boundary map, but now you need to subtract the image of the larger simplices at the next length scale. So this is epsilon prime. It's important, but you only want to fill holes that are somehow relevant, so you need to somehow restrict this to the space that you care about. So if you would just subtract this dimension of this image, then you might be subtracting simplices that are somehow far apart from what you would normally care about. So somehow this is the right object to look at. And basically, this is all that you need to know about how to compute Betti numbers. It is some dimension of some subspaces. And now the question is how to deal with these subspaces in a quantum computer. Well, a quantum computer is good for linear algebra, so it's hopeful. And okay, this is just a summary of results so far before I go to details. So the first paper by Lloyd et al. That was the first to give some algorithms, and well, they had some polynomial complexity in these relevant parameters, which is delta is the precision to which you want to estimate the Betti number, and then there's this gap. These are all sorts of gap parameters, these lambdas, that are somehow gaps of the spectrum or of the boundary operators, more precisely in this case the singular values, and then Betti numbers, and then number of all possible number of simplices and so on. And while there was some improvement in the complexity and also improvement in applicability, because initially people only looked at single Betti numbers, but as we discovered, in practice we care about persistent Betti numbers. The first work had quite high complexity, but they showed that it's possible with, in principle, this exponential speed up if you have a normalized Betti number estimation. And well, the previous talk gave an algorithm which is efficient than the previous ones, but only considered the normal, the actual simple Betti number case. And we have a similar algorithm which has two main improvements. We can track persistent Betti numbers now, and also we have an exponential saving in the space. So once again, we looked at the case when these simplices and holes that we look at are kind of low dimensional. So dimension, I don't know, 3, 4, some constant. And then you can save a lot in actually how you store these simplices. And again, this seemed to be the practically relevant regime, so that we focused on that. And also, like these are just rough expressions for the complexities. The actual complexities are somewhat more complex, but just to give an idea about overall scaling for you. Okay, and so one thing which should be noted, like all these gap quantities are just somehow gaps of this boundary operator or some variant of that. But now we have a new parameter, which was something like, I think, lambda 2 here. But in our case, we didn't buy this. This somehow comes from this intersection. In the previous slide, we had to intersect these two kind of subspaces. And somehow, how you intersect these subspaces and what is the angle of the intersection, that is a new gap parameter which appears in our analysis. And if you don't care about persistent Betti numbers, then this is just 1. So this basically disappears in the special case. General case, you need to also worry about this. Okay, and then, well, there are also classical algorithms which are optimized for this, like the textbook approach has some matrix multiplication exponent in it in terms of the number of simplices that are present. And and there's the power method, which has a nicer complexity but has a gap dependence. And originally, this power method was only worked out for the simple normal Betty number estimation, but we extended this with essentially the same complexity to also compute persistent Betty numbers, which is unfortunate. It works because it means that in the regime that we care about, like relatively small Betty number, relatively small dimension, it means that we don't really get a more than quadratic speedup in that regime. Too bad that it's not enough to, once you improve a quantum algorithm, you figure out an analogous classical algorithm, it suddenly matches. First, you are happy that it's a quadratic, it's like a quartic speedup, and then you work harder, and it's only a quadratic speedup, so it's not always good for working too much on a topic. And there are also Monte Carlo algorithms that were on Werner's work also contained, and Simon Appers and Couters has also recently a similar approach. Now, it should be noted that it can be potentially interesting when you want to normalize Betty numbers, but somehow have a very small gap or some other parameter of your object is especially nice. Otherwise, these algorithms can blow up exponentially, but in some interesting regimes, you can also get non-trivial speedups. Okay, and then a few words about our techniques. So most work considers this unary encoding of the simplices. So if this is every qubit is standing for a vertex, and it's just incidence vector of the present vertices. Whereas the compact encoding is that you just store a list of the label of these vertices. It doesn't look very advantageous in this small example, but once you have thousands of vertices, then it's very much a big saving. And then, well, we need to somehow quantum mechanically encode this boundary operator, which we do. We either use the direct encoding, this long encoding of prior work by Karandis and Prakash, or we show how to do it with a slow overhead, but using this exponential saving. And then we also compute what's the complexity of implementing the overall restricted boundary operator, and these are some space and circuit complexities. And this depends on number of dimension of the points that we have, and also the bit complexity of these things, which can be quite high. But then we also mentioned that actually you can first improve the number of bits stored by just doing a dimensionally reduction. So your many points live in a high dimensional space potentially, but you can just reduce it to map it to or map it to a much lower dimension, and you don't need to work with that much data after all. So that's a thing to remove these parameters essentially that we mentioned in the paper. And while the algorithm is just converting the block encodings of these boundary operators to projections to the kernels of these operators. And then you just do it by QSVT. You need to know the gap of this operator, and then you can map the spectrum to basically a binary spectrum approximately. And then, well, in case persistent numbers, we also need to care about this intersection of subspaces, which we do by taking a product of two projectors, and once again applying QSVT on this to map the potentially non-trivial spectrum back to 0-1 spectrum. And here we get a quadratic improvement in terms of the gap along the lines of Szegedi quantum walks, which can be applicable here. That's why we only have a square root dependence on this latter gap. And finally, we use amplitude estimation on a random trial state to estimate the dimension of this subspace that we end up with at the very end. This is the very rough overview of the algorithm. And the classical algorithm with the power method is basically doing the same thing. The observation is that we are doing some polynomials of some matrices and activate some states. Now you can do the same thing on a classical computer, but every time you just keep track of the entire vector. And because your matrices are sparse, you can just use sparse matrix vector multiplication, which means that you only pick up a linear factor in the dimension. And basically just you do the same thing as the quantum algorithm does, but always write out the state, basically. And that's how we get this power method-based algorithm for persistent numbers, basically copying our quantum algorithm and keeping track of the state using sparsity. Okay, and I think I managed to get on time to the open questions. Well, I think open questions are that shared with other talks, but let me say that again. So we should find an instance where normalized Bethe numbers matter, because that's where we can hope really superquadratic speedups. That's an important thing to understand. And while all these algorithms depend on some spectral gaps of these boundary operators, and we don't really have good methods to bound them, so that would be also an interesting question how to do that. And then, well, the last question is along the lines of these Monte Carlo algorithms. How far we can push these techniques? Are they certainly blowing up exponentially, or how mildly they blow up? This is, I think, a very interesting research line, and we have 2 recent papers, but I think there are many more questions, and they can potentially be improved. So these are the main open questions, and thank you.
Thanks for the talk. So if you go back to the table of complexes, so I don't know if you mentioned it, yeah. So the time complexes, they're a bit like hard to sparse. Can you comment more about that? Are you missing or losing something on the time complexity in order to gain exponential advantage on the space?
Sorry, I didn't fully understand. Which factor you mean?
The time. So how does your time complexity compare to the previous ones? Because I mean, it's hard to see if they're worse or better.
Oh yeah, okay. So, well, so here I listed the one which is exponential saving in terms of space.
Yep. Mm-hmm.
If we use the more verbose encoding, we get, I think, basically the same complexity as Verran got. Mm-hmm. But in the case of safe space saving, it's it's a bit worse. Okay, so how it compares? So this gap is essentially the same as this gap. Okay. Delta is the precision the same. You know, this only appears in the persistence. It seems to be necessary. And while K, well, we care about the case when it's low dimensional holes that we care about. So I think about K as a constant in practical purposes, as this is the Bethe number that we care about and the possible number of all simplices. So these are very similar parameters in all appearing. And then this n is the over number of points, which is maybe slightly worse here, but this is much smaller than this n choose k plus 1 anyway. So, I mean, important to keep track of, but yeah, somehow this is the worst thing in this complexity that it appears here. That's shared with all of them.
Okay, thank you.
Sorry, this is just a clarification question. So you said K is small and constant in practice. If I'm not wrong, the last speaker mentioned that you want the clique number to be large, so for advantage. So could you comment on that, please?
You mean that the number of cliques that appear in the complex? That's the clique, no?
So I believe we wanted
Okay, yeah. Well, I guess for advantage you want a large clique number, and that's what you said. And as far as I saw, most paper in practice looked at relatively lower dimensional things. So I agree that for advantage, okay. So once again we ask the question for the kind of parameters that people seem to apply this technique in practice. What is the speed up we get there? And well, basically we can conclude that no bigger than quadratic. And obviously, if you want the advantage, then you should look at parameter regimes which are not common in the literature, and there you can hope for a larger speed up. I absolutely agree with that.
Sorry, yeah, that was just the clarification. Thank you so much.
Other questions for the speaker? Okay, if not, let's thank András again.